the 3 bars here, and big R, which remember the U, your wave function, was a product of 2 functions, big R and a spherical harmonic Y, Ln. So redefine big R now is chi over rho. Right? You've got rho defined here, so you know what rho is. And so, in a sense, you're defining what chi is. Chi is big R rho, in effect. Okay? Now, why do that? Because it simplifies this equation, the Schrödinger equation, which boils down to this. Okay? And I've asked you to do homework. I've asked you to do that. It's not too difficult. So, rewrite your equation x circle, the Schrödinger equation, and get this. Right? So do that. And now we can tackle this and solve that. So if we can solve for chi, then we know what R is. I'll put it this way. If we can now this chi here will depend on rho. Right? So just look at this second order differential equation. Obviously chi will depend on rho. All the other things are constant. Right? For a given L, assume a given L. So chi will depend on rho. Alright. So chi will be some function of rho, that's a function of rho, therefore R, big R, will be a function of rho. Okay, and so if you know what R is, in terms of rho, you can find what little r is in terms of rho. Well, if you know what rho is, you can find what little r is by using this. Alright. Okay, so things boil down now to analysing this equation. And once again, so much of wave mechanics, Schrödinger's equation, sooner or later boils down to solving differential equations. Right? So here we are again in that situation. So we need some approach, some that's one of the disadvantages of making home movies. Right? When you, well, I don't know. I've been in a situation when I was a waged professor, where there were workmen. While I was giving classes in a classroom, and there were workmen working on another floor of the building, and it was noisy, just like this. So maybe not so different. Okay. So we need to solve this equation. So we need some essential device, some trick, some method of attack, some approach, and that's often where the brilliance comes in of somebody who finds a new way to solve a DE, or solves new DEs due to some new trick. Well, here's the trick. Okay, so concentrate, because it's a bit of a brain teaser, if you like, but it's the essence of solving this equation. Here it is. Assume that we have a solution, chi, to this equation for a given L, for a given value of L. So let's say that value is k, for a given integer. Now, L is an integer. So let's say we know that chi of little k is a solution to this equation for a given L. Right? So if your L is k here, so you'd have k and k here, then psi of k is a solution to this. Imagine that's the case, right? So psi of k is a solution to this equation. Then, right, so it's an if-then type reasoning. If psi of k solves this equation, then this term here is the solution to psi k plus 1. In other words, when L is k plus 1. Okay? That's I ask you to show that as homework. Prove that that's the case. So how would you do that? Well, you just put this term in here and here. Work it out. Now your L in this case will be k plus 1. So you put k plus 1 here. You plug this as here and here because you're told that this is the solution when your L is k plus 1. One more. Okay? And show that this left-hand side, where the L is k, you put this into here and here for your chi, and then show that this left-hand side is 0. Right? It's not equal to it. And if it is, if this is 0, that shows that this term here is the solution to this equation, but interestingly, when L now is 1 larger. Right? It's now k plus 1. Before it was k. And you may say, so what? Well, it means that if you know what k naught is, it means you can find k1. And if you know what k1 is, you can find k2. Right? So it's a kind of inductive type argument. So by increments, you can find all of your chi's, chi L's, so long as you know what chi 0 is. Right? So think about that. Do the homework. Prove that that's a solution for k plus 1. One more. Right? Given that chi of k is the solution to this for L is k. All right. Okay. So what is chi of 0? The lowest term. Well, chi of 0. So that means k is 0. That means L is 0. Okay. So L is 0. So this whole term just drops out, and then you've got a particularly simple d. Then you've just got d squared chi d rho squared plus chi is naught. Well, that's just the simple harmonic equation. So chi is either sine rho or cos rho. Right? That's pretty trivial. So we know we have a value for chi naught, and then with the reasoning we did before, if we know what chi naught is, we can find chi 1. And if we know what chi 1 is, we can find chi 2, and so on. Right? So we know we can solve for all of chi L's, for all L, all integers L. 1, 2, 3, dot, 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 dot. Right? Now, okay, so now chi naught boils down to either sine of rho or cos of rho. So are both acceptable? No. It works out that cos rho you reject because, remember the mathematical sign, it's an upside down therefore. Therefore sign is a dot and then 2 dots underneath, like a triangle pointing up. And the because is you take your triangle pointing up and you make it turn down, like here. So that's the because sign. Do I have a therefore? Yeah, here's the therefore, right? And therefore the position, blah blah blah. Okay. Right. So you reject cos rho because, why is that? Because it blows up. Is that right? Let me just check the reasoning here. So why is that? So as R goes to infinity, so R goes to infinity, so that means your rho could go to 0. So rho, R goes to infinity, so rho could be 0, right? So that's 0, R 0, and R 0 is inside your sphere. And you don't want, so that So from the text, so you get a gradient discontinuity. Remember, does it make sense? I'm just trying to think, what is that gradient discontinuity? Remember, at a boundary, you have certain conditions, constraints you impose on your wave function. Like in this case, at the boundary r equals a, the wave function has to be 0. So the gradient has to be 0. So I'm not quite sure. Well, you know, I'm going to put that as homework as well. Think about that. So I'm just giving you the result. This is from the text. You reject the cos rho solution, so you're only left with sine of rho. And the reason why this cos rho is unacceptable is because you get a gradient discontinuity. The two. Now, where is the discontinuity? I guess at the edge of the sphere. Does that make sense? Yeah. I haven't thought that through in detail. Anyway, I'll leave that as homework for you. Think that through. Why is this rejected? All right. So that leaves you with sine of rho, and so now we have chi of naught. It's just sine of rho. So we can use this kind of trick to find chi of 1, chi of 2, and hence we have the solutions to this equivalent of a Schrodinger equation.